The reflection appeared first in the tide monitoring feed. Not as distortion, not as glare, but as a second luminous body resting on the water's surface beneath the pier, perfectly circular, sharply defined, and positioned several degrees away from the actual moon above. The coordinates were fixed along a coastal research pier used for long-term tidal gradient analysis. Optical calibration logs confirmed sky clarity. There was only one moon present in the atmosphere. Yet the water displayed two. The initial assumption centered on surface interference. Minor wave interference can refract light into elongated or duplicated forms, especially under low-angle illumination. That explanation collapsed within minutes. The second reflection maintained geometric stability independent of wave motion. Ripples passed through it without distortion. The reflected disk did not fragment, stretch, or scatter. It held position as if anchored beneath the waterline. Camera angle adjustments produced no change. The reflection remained visible even when the viewing perspective shifted along the pier. Standard reflective behavior requires alignment between observer, surface, and source. That alignment did not apply here. The second moon remained fixed relative to the pier itself, not to any viewing vector. A divergence began to form between optical expectation and observed persistence. Surface analysis confirmed normal tidal behavior. Current velocity, salinity distribution, and temperature gradients remained within expected parameters. No suspended particulate density was sufficient to generate secondary imaging effects. The water itself retained its physical properties. Only the reflected geometry deviated. Field technicians deployed polarized filters to isolate surface glare. The primary moon reflection dimmed accordingly. The secondary remained unaffected. Light polarization had no measurable influence on its intensity or clarity. It behaved as if its source did not pass through the same atmospheric or optical pathway. Further imaging introduced spectral analysis. The visible band response of the second reflection matched lunar reflectance profiles. Infrared readings showed corresponding thermal consistency with reflected solar illumination. The object behaved in every measurable wavelength, like a legitimate lunar reflection. Except for one constraint. There was no corresponding object in the sky. The first internal disagreement emerged at this stage. One team proposed subsurface luminescence, a spherical source beneath the water generating upward reflection. That interpretation required a physical body at depth emitting or reflecting light consistent with lunar albedo. Sonar scans were initiated to identify any mass beneath the pier. The scans returned uninterrupted water column profiles. No object, no density anomaly, no suspended structure. The reflection persisted in the absence of any measurable source. Over the next observation cycle, tidal elevation increased. The waterline rose along the pier supports by measurable increments. The second reflection did not shift with the changing surface height. Its position remained fixed relative to the pier's structural coordinates rather than the water surface itself. It appeared bound to depth, not to surface. This inversion introduced a new constraint. Reflections, by definition, are surface phenomena dependent on incident light angles. Here, the phenomenon maintained stability as if projected upward from a consistent subsurface origin that did not move with the water. Divers were not deployed immediately. Instead, a controlled lighting test was conducted. Artificial light sources were directed toward the water at varying intensities and angles. These sources produced expected reflective behavior, scattering, diffusion, and angular dependency. The second moon remained unaffected. It neither intensified nor diminished under additional illumination. The behavior suggested independence from incident light. At this stage, long-exposure imaging revealed a subtle discrepancy. The primary lunar reflection exhibited micro-oscillation consistent with surface ripple frequency. The secondary displayed no such oscillation. Its edge remained fixed across exposures, indicating positional stability not influenced by surface movement. The water moved. The reflection did not. Acoustic monitoring introduced the first environmental deviation. Sound propagation across the water surface exhibited localized dampening directly above the second reflection's position. Waves produced by controlled mechanical disturbance showed reduced amplitude within a defined circular boundary, matching the reflection's diameter. The surface did not flatten, but its energy dissipated differently within that region. The water behaved as though interacting with a boundary that was not physically present. This effect expanded slightly over successive measurements. The dampening radius increased by measurable increments, thou. GH. The visible reflection retained its original size. The boundary between normal wave behavior and suppressed propagation remained sharply defined. The anomaly began influencing physical processes beyond light. During the following night cycle, an additional inconsistency emerged. The actual moon shifted position across the sky as expected. Its reflection tracked accordingly across the water's surface. The second reflection remained fixed. The two reflections diverged spatially over time. By midnight, the separation between them became visually obvious to the naked eye. Observers standing along the pier reported a stable luminous disk in the water that did not correspond to any celestial alignment. The phenomenon was no longer restricted to instrumentation. It became externally observable. A decision was made to deploy a submerged camera system directly beneath the reflection. The unit descended through the water column, transmitting continuous visual data. As it approached the depth corresponding to the reflection's vertical axis, the feed began to degrade, not through signal loss, but through visual inconsistency. The camera recorded water, but the geometry no longer aligned. Light gradients within the feed suggested a horizon line forming beneath the surface. The angle of illumination shifted in a way inconsistent with overhead light sources. The apparent direction of brightness originated below the camera, not above it. The descent halted. Further movement risked equipment loss due to navigational uncertainty. The feed stabilized once the camera was raised several meters. Above that threshold, normal underwater imaging resumed. Below it, spatial orientation became unreliable. The anomaly introduced a vertical inversion in perceived depth. This was not a reflection. It was a region where directional light behavior contradicted the position of its source. Over the next operational cycle, a temporary stabilization occurred. Measurements plateaued. The reflection maintained consistent size and position. Acoustic dampening ceased expanding. The submerged camera, when held just above the distortion threshold, produced stable imagery. This led to a provisional classification: localized optical anomaly with secondary acoustic interaction. That classification lasted less than 6 hours. A routine recalibration of tidal sensors produced an unexpected reading. Pressure sensors mounted along the pier supports indicated a localized reduction in hydrostatic pressure directly beneath the reflection zone. The magnitude was small but consistent across multiple sensors. The water column in that region exerted less force than surrounding areas. This contradicted depth-based pressure distribution, which should remain uniform at equal depths. The anomaly was no longer confined to light or wave behavior. It affected mass distribution. The next step involved introducing a calibrated object into the region. A weighted marker was lowered into the water directly through the center of the reflection. Its descent was tracked via tension measurements and visual feed. The marker entered the normal water column. Then, at a specific depth, resistance changed. The line tension decreased abruptly, as if the object encountered reduced density. The marker accelerated downward for a brief interval before stabilizing again. No obstruction was recorded. No collision occurred. The object passed through a region where water behaved as if it occupied less volume than expected. When retrieved, the marker showed no physical damage. However, the depth reading associated with its lowest point did not match the length of deployed line. A discrepancy of several meters remained unaccounted for. The object had traveled farther than its physical constraints allowed. The anomaly demonstrated independent influence over physical depth perception and measurement. At this point, the second moon remained perfectly intact on the surface, unchanged, stable, and sharply defined. It did not flicker. It did not shift. It did not respond. But everything beneath it no longer behaved consistently with the rest of the ocean. By the end of the observation period, the conclusion became unavoidable. The luminous disk on the water was not reflecting something above. It marked the boundary of something below. And that boundary did not align with the physical structure of the sea. The first structural concern emerged when the pier's load distribution shifted without visible cause. Weight sensors embedded in the support columns began reporting asymmetry across a span that had remained stable for years. The deviation was not large enough to trigger alarms, but it followed a consistent pattern: reduced load directly above the reflection zone, and a compensatory increase along adjacent supports. The structure was redistributing weight around something that did not register as a physical obstruction. Divers were cleared for controlled descent under strict tether constraints. RI was performed several meters offset from the anomaly's vertical axis. Visibility remained standard until the descent approached the same threshold previously identified by the submerged camera. At that depth, orientation became unreliable again. One diver described the light field shifting in a way that altered directional reference. The surface above no longer appeared as the brightest point. Illumination seemed to originate from a lower plane, diffused but consistent, as though a secondary sky existed beneath the waterline. The diver did not descend further. Instead, a lateral approach was attempted. Movement parallel to the anomaly boundary produced an observable effect. The reflection above shifted position relative to the diver's location. It did not track the diver, but it maintained alignment with the pier's structural grid, as if the anomaly's geometry was anchored to the infrastructure rather than to the surrounding water. This alignment introduced a new constraint. When maintenance crews repositioned a floating calibration platform along the pier, the second reflection adjusted its position the following night. The shift was small, less than a meter, but it matched the platform's new coordinates. No direct interaction occurred. Yet the anomaly reappeared in alignment with a structure that had been moved hours earlier. Subsequent observations confirmed the pattern. Temporary equipment placed along the pier influenced the reflection's position on the next cycle. Removal of that equipment resulted in the reflection returning to its prior alignment. The behavior created a consistent relationship between infrastructure layout and anomaly positioning. No causal mechanism could be identified. The acoustic dampening field began to fluctuate during this phase. Instead of expanding uniformly, it pulsed, contracting and expanding within a narrow margin. These fluctuations did not follow tidal cycles or environmental conditions. They occurred in intervals that aligned with monitoring attempts. When sonar sweeps intensified, the dampening radius contracted slightly. When monitoring paused, it returned to its previous extent. The pattern repeated across multiple observation windows. The anomaly maintained physical presence, but its measurable influence varied depending on the level of scrutiny applied to it. This introduced a layer of instability into the investigation. Efforts to map the subsurface region beneath the reflection produced inconsistent results. Depth readings varied between scans, even when equipment calibration remained unchanged. In some passes, the region appeared shallower than surrounding water. In others, it extended beyond expected seabed depth. The seafloor beneath the pier did not physically move. Yet its measured position changed. A temporary dead end emerged at this stage. For nearly a full observation cycle, the anomaly exhibited no further escalation. The reflection remained stable. Load distribution held steady. Acoustic behavior normalized. The subsurface distortion did not expand. It appeared contained. That assessment ended when the tide reversed. As water receded, the exposed portion of the pier extended further above the surface. The primary moon reflection shifted accordingly, maintaining its expected geometric relationship with the sky. The second reflection remained fixed at its original coordinates, now positioned farther from the waterline due to the lowered surface. For a brief interval, the reflection appeared suspended below the pier, no longer touching the water. It retained its brightness. It retained its circular form. But it no longer occupied the surface it had been associated with. Observers standing on the pier reported a visible gap between the water and the luminous disk. The effect persisted until the tide rose again, at which point the reflection reconnected with the surface as if nothing had changed. The anomaly had decoupled from the medium required for reflection. This event marked the transition from localized inconsistency to systemic contradiction. The next phase involved interaction with navigation systems. Vessels approaching the pier reported minor deviations in depth readings when passing through the anomaly's projected radius. Sonar altimeters indicated temporary increases in water depth that did not correspond to charted seabed profiles. The deviations were brief but repeatable. Each pass through the region produced a momentary expansion of perceived depth, followed by immediate return to baseline readings. Navigation protocols were adjusted to route vessels around the affected zone. During one controlled transit, a vessel was directed to pass directly through the center of the anomaly at reduced speed. Real-time monitoring recorded a synchronized response across multiple systems. Hull-mounted sonar registered increased depth. Surface-based LiDAR maintained unchanged waterline measurements. Internal inertial systems recorded no vertical movement. The vessel did not descend, yet its instruments indicated that it had passed through a region of deeper water. The contradiction could not be resolved through calibration. The anomaly had begun influencing multiple measurement systems simultaneously, without altering the vessel's physical position. At this stage, the second moon remained visible from shore. Public observers noted its presence but attributed it to atmospheric effects or optical illusions. No official explanation was issued. The phenomenon did not disrupt daily activity, but it introduced a persistent visual inconsistency along the coastline. The anomaly had entered the category of publicly noticeable but unexplained conditions. A final verification sequence was conducted using synchronized multi-angle imaging from aerial drones. The objective was to determine whether the second reflection existed as a consistent geometric feature across independent viewpoints. The results confirmed its stability. From every angle, the luminous disk maintained consistent size, brightness, and position relative to the pier. It did not distort with perspective. It did not shift with observer location. It existed as a fixed element within the environment, not as a reflection, but as a spatial boundary. In the final operational phase, long-term monitoring protocols were established. Continuous tracking of load distribution, acoustic behavior, and depth variance was assigned to automated systems. Navigation charts were updated to include a cautionary zone around the pier. The anomaly was not removed. It was incorporated into operational models. The water beneath the pier continues to display two moons. One corresponds to the sky. The other marks a region where depth does not align with distance, where pressure does not match volume, and where light originates from a direction that does not exist within the observed environment. The coastline has adapted to its presence. Fishing routes curve slightly away from the pier. Nighttime observers pause longer than expected when crossing its line of sight. Instrumentation records it without interpretation. The second moon remains in place, fixed to a geometry that does not follow the surface it appears upon. It does not expand. It does not vanish. It remains aligned with the structure above it, independent of tide, weather, or observation. And beneath it, the sea continues to hold a depth that cannot be measured consistently, only encountered.